Okay, so let's get started. I realize that this is not the usual day that we meet, since it's a Tuesday afternoon, but that's the schedule, so here we are. And I also realize that we're kind of at a time in the schedule or the semester where it's kind of getting hard, right? You're having some of you are having a difficult time with exams and just all the things that are going on. And I was in the lab the other day in Marcus, and I saw this note up on the board. Someone had written, "Currently regretting engineering, should have done business." And someone else wrote, "Don't worry, good times to come." And I wanted to put that statement here on the slide because I just wanted to, I want to honor the sentiment, and I wanted to pay respect to, the concern that someone may have. Now, I suspect it was written somewhat in jest, but at the same time, I think a statement like this on our lab, and it could be from this class or from junior design project, doesn't matter. But the point is, it's a difficult time right now. I get it. I do get that. And with regard to this class, some of you are sort of cruising right along, and you've got all your software tools going just fine. And you got the code going, and that's fine. Some of you are still trying to get those tools going. You're still trying to get the compiler. You're still trying to get things set up on your computer, and you may be trying to make sense of all this GPIO stuff. It will get better, and it'll get a lot more fun once we get past some of this basic stuff. So what I want to say is, if you are sort of, whether you're regretting studying engineering or whether if you're regretting studying engineering, email me. And I'm happy to chat with you about that. There are certainly plenty of times when I was an engineering student at UMass decades ago when I said, geez, did I do the right thing? And indeed, many times throughout my career, I said, did I do the right thing in studying engineering? But I always come back to, yes, this has been a really enjoyable career for me. But if you're having a rough time, if you're questioning engineering or this course or whatever, feel free to email me, and we can set up a time to chat. And we can have a nice chat, and I'll promise I'll be nice to you. And spending a little extra time talking about this, I did spend a stint as the academic dean for engineering. And during those years, I felt that I was responsible for the academic success of, more than 2,000 engineering students. And so I have a fair bit of experience talking to students, sort of coaching students when things get rough. So if you're at that point, you want to chat, you feel free to email me, and we can set up a time to chat. And whether it's about how do you set a pin on a port, or how do you make code work, or am I in the right major? I can't necessarily answer that, but I can try to give you the benefit of my experience and perspective. And I'm also a parent of 3 kids who have gone through college. So so just know that if you want to chat, don't hesitate to reach out. Okay. Okay. Let me tell you where we are today and tomorrow. We're working on GPIO. This is the basics: how to do input and output from a microcontroller device on an Arduino Uno, and then later on we'll move just to the chip itself and not the Arduino Uno. This is the basics. This is the basic stuff we have to get down. And once we do this, we can start to have more fun with this stuff. To do the homework assignment that you have, you need today's material and also tomorrow's material in order to be able to do homework assignment number 2. And I have seen some of the questions coming in from Piazza. How do I do this? We're going to cover that today, and also tomorrow. You'll need tomorrow's material too. So into the slides here. So some things I want you to be doing and be aware of. So first of all, be reading the text. It's sections 7.1 through 7.3. And then try out some of the example problems there if you haven't already done that. Okay. Some of you asked that I post a video demo showing me building a blinking LED with a switch. I've done that. That's a YouTube file that you'll find posted to this week's Moodle tab. The code that's in that and also the make file are also posted there, so you'll see them. So if you want to see me go through building a circuit and encoding it, it's there. I've changed the due date on the labs. Instead of labs being due on Sunday at midnight, the problem with that is, I mean, the good thing about it is you sort of have the weekend. The bad thing about it is you have to use the weekends for your assignments. But the imbalanced thing about that is that we don't really have many resources, teaching team resources for you on the weekend when a lot of you are working on your assignment. Our teaching team resources tend to be front loaded in the beginning part of the week. So I'll be changing the due dates of assignments to Thursdays at midnight, a minute before midnight. That way, if you're working on a Monday, Tuesday, Wednesday, Thursday, the TAs and I are available in our office hours, okay? Okay, the next thing I gotta say here, this is never fun, but something we gotta do. We're gonna have a midterm, and it's gonna be on Wednesday, March 9th. That's the week before spring break. And we'll do that via Moodle during the class hour, okay? If you are someone that has accommodations set up, you're entitled to accommodations, time, and so forth, email me and we'll work to set that up. But this will be an exam via Moodle. You can take it from sitting wherever you are right now. You can be at home, you could be in the classroom, you could be in a cafeteria, you could be wherever you want to be to take this thing. You just have to work alone and you don't use Chegg and things like that. Okay. One more thing is, if you haven't already done so, I want you to pick up your kit in the lab. And we've opened up a parts depot in the lab, and I'll show you what that looks like. So I want you to check the inventory in your kit against the parts list that I've published to Moodle. So this week's Moodle tab has a spreadsheet that shows you all the things that you should have in your kit. And if you're missing something, go into the lab and get it. And now let me tell you, I'm going to show you some pictures of the parts depot. This is your parts depot, all right? I have lots of parts in there, things that you can come and get, no questions asked, anytime. These are things we bought with your engineering fee. So this is your parts depot and your parts, and you are welcome to come into the lab and get whatever you want, whenever you need it, at any time, okay? Or at least any time the TAs are in there to let you in. I'm going to show you pictures of the parts depot so you know what I mean. Okay, and then this last point, things are going to get more complicated in the class. They'll get more fun. We'll be doing more useful stuff, but it's about to take a turn after lab 2, after this assignment, and it's going to get rather more complicated because we're going to be doing lots of interesting things, building digital thermometers and building distance sensors and talking to other computers via serial ports. So at this point, I want you to use this week to get your stuff working. So you want to have visual code working. You want to know what to do with make in the make file. You want to have the compiler working. And if you have trouble, come see us. During our office hours, use Piazza, but get the problems taken care of this week. Okay, in the lab, you go in there and set up on a number of benches. One bench, we have the small components, LEDs, resistors, switches, some transistors in there, the little piezo speakers, RGB LEDs. Much of this, you don't even know what you're going to use. You won't even know what you'll use these parts for, but you do have an inventory on Moodle. You can take a look at it. If you don't have these pieces, come in and get them, okay? What else? We have other things in there. I have pocket multimeters in there. If you want a multimeter for your experiment, come get one. They're yours to keep. If you're missing anything off of the list, come in and pick them up. We have another bench here that there are some things that some of you may actually be missing. When we were building the kits, I know some of the kits were short on a couple of components. There's a small organic LED display that's in one of these boxes. If your kit doesn't have one, come get one. And you need to have 2 USB mini cables. You'll be using these later on. So if you don't get them now, you can get them later on. Also, we've got different sized breadboards. We've got some little tiny breadboards if you need those. So come on in. This is your stuff. So you're welcome to come in anytime and get these things. That's the parts depot. Okay, now let's get into where we were talking about programming these IO ports. And so you've seen this slide before. And all I want to do is I want to point out when we talk about a port, we're talking about there's the physical pins, right? And which we'll designate as, for port D, it's P0 through P7. Okay, so that refers to the pins themselves. Then we have these registers, We have port D, that's the data register. We write something to that so that we can assert a high or low on one of the pins. There's the data direction register. We make that high or low depending on whether we want a pin to be an input or an output. And because, you know, these same pins can be used as outputs where you're turning on LEDs or you're turning on something else, or they can be inputs where you're reading switches and other things. And then the pin register is the one that actually reads the value of those pins. So it's a combination of the physical hardware and then these three registers that we use to interact with the pins. Okay, we went through this whole slide last time, so I won't elaborate on it other than to say when we're programming in C with our AVR GCC compiler, we can't address the individual pins by themselves. The language only allows us to program at once all of the pins in the register. So it's a statement like this: port B is equal to 0xFF, right? And FF is just a string of 1. So we have to set all of those bits. So we have to come up with a way when we want to. It's very important that we're able to set those individual pins without bothering all the other pins, right? Because let's suppose we're using some of the pins in the register to blink LEDs, and the other pins we're using to control a fan or a thermos or a heater based on a thermostat. You know, we want to be able to allocate different pins to different purposes, and it's important that we be able to get in and toggle or set or clear individual pins by themselves. So the dilemma that we have is when you do a command like this, you have to actually, you know, write an 8-bit word, and that's going to address all 8 bits of the port. So how do we get in and toggle the individual bits? How do we set individual bits high and low? Well, we do that with logic, and where we're going is commands that look like this. And this is sort of what we started to set this up last time. We'll continue to do it this time. These two panels, they both mean the same thing. So there's two ways of saying the same thing. Don't try to make sense of this yet. Okay, this is what you'll be doing. I'm going to build on this with the rest of the slides today and also on tomorrow. And this is pretty complicated because we're really at the bit twiddling. We're really figuring out how to go in and talk to individual bits, you know. And so we're going to be looking at statements like look at that mess right there. I mean, it's not really a mess, but there's a lot of shorthand there. What you're doing is you're saying port B is equal to port B and some of this other stuff. So that says port B is equal to port B and the complement of the number 1 shifted to the left by 5-bit positions. All right, now let's build that up in the next slides. Okay, so we saw this slide last time. I'm just reviewing Boolean logical operators that you played around with these in ECE 124. And then we kind of got to this point last time, and we said, okay, with these operators, these are bit level operators. So the idea is, let's suppose I start out with a variable, all right, occupying a byte of memory, and let's suppose it has this pattern of 1s and 0s. And then let's suppose I take it and I AND that with this. So in other words, I'm just doing 1 1 1 1 1 0 0 0 and 1 0 0 1 1 1 1 1. That AND is a bit level operator. So it's going to do an AND gate function on each and every bit. 1 and 1 is 1, 1 and 1 is 1, 1 and 0 is 0, you know, and so forth. And the rule here, the takeaway is, if you AND with a 1, you'll get the original bit value back. If you AND with a 0, you get 0. So we can use this to clear any bit in a byte. And we'll get to that on the next slide. It's called using a mask. But that's the idea. Based on this observation, if you ever want to clear out, that is set to 0, any particular bit in a byte, you AND it with a bunch of 1s and a hole, a 0, where that particular bit is you want to 0 out. And that has the effect of leaving the other bits alone and zeroing out a particular bit. Okay, and we'll see that on the next slide. Okay, if we do the byte-wise OR, okay, let's just look at all the combinations. 0 or this bar here means OR. Okay, it's one that you're you're probably have not used before you started doing C, but a couple of weeks ago we looked at using two of those vertical bars together. That's the logical OR. One of these vertical bars is the bitwise OR. So 0 or 0 is 0, 0 or 0 is 0, 0 or 1 is 1. Okay, 1 or 1 is 1. And the rule here, the thing that we can the rule that we can infer from this is that if we OR a bit with 1, we'll get back a 1. If we OR with 0, we'll get back the original bit. So what that says is, let's suppose that we start out with a byte, right? And I want to turn some of these into 1s, but I don't want to, I want to leave the rest of them alone. If I OR them with a mask, I OR them with another variable that has a 1 in this position here, that'll cause that to become a 1, and it'll leave all the rest untouched. And you'll see that on the next slide. Okay, this next one is getting really kind of fancy. This is the exclusive OR. And you may remember what the exclusive OR is, from the truth table. If we go back and look at the truth table for the exclusive OR, if A and B are both 0, then A exclusive OR B is 0. Okay, if A is 0 and B is 1, then A exclusive OR B is 1. If they're 1 and 0, then the exclusive OR is 1. And if they're 1 and 1, the exclusive OR is 0. In other words, the exclusive OR is either one or the other, but not both. That's the idea here. If they're 2 zeros, then the exclusive OR result is zeros. If they're 2 1s, the exclusive OR result is 0. And if one or the other, but not both. So what happens when we apply that over here in this case? Well, we're going to start out with some initial byte. And I'm just going to exclusive OR every single bit. And let's just see what happens. 1 exclusive OR 1 gives us 0. 0 exclusive OR 1 gives us 1. 1 exclusive OR 0 gives us 1. Okay. The rule here, what do we take away here? If you exclusive OR with a 1, you'll toggle. What that means is if you started out with a 1, it becomes a 0. And if you started with a 0, it becomes a 1. So if you exclusive OR, you toggle a bit. And this is important because one of the ways we can make an LED blink is toggle it. Every time we go through the loop, we toggle it, right? So toggling becomes an important thing where every time you go through it, you're going from 1 to 0. So what we're seeing here is we can use these bitwise operations. We can use the one on the far left here, where we take a value, we AND it with a mask, and we can cause a certain bit to be cleared. Right? You sort of AND it with a hole in it, and you can clear a bit. You OR it with a bit that has a 1 in it, and you'll end up setting that bit. Or you exclusive OR it with a 1 in a certain bit position, and you'll toggle that bit. And so this next slide just sort of develops that idea here. So the idea is, how do we go after and clear a particular bit? Say there's one bit that we want to kill. I don't mean kill it, but I mean I want to clear it, right? So let's suppose that I have this bit, this 1, and I want to turn that to a 0, but I don't want to touch any of the others, right? What I would do is I would AND that with this is called a mask, and I would have a 0 in that position. And that has the result of zeroing out that bit, but leaving all those other bits unaffected. Okay, so you can clear a bit by using an AND mask that has a 0 in the bit position where you want to clear. Okay, and so it's not that complicated when you unpack it all, but there's a whole lot of it, right? There's clearing a bit using an AND mask, there's setting a bit using an OR mask, there's toggling a bit, so there's a bunch of these rules. Once you've got them figured out, and the way you actually make sense of them is by coding them up, right? But I realize I'm throwing them at you with all this PowerPoint, so I know it's kind of hard to digest it, make sense of it in real time. Oh, by the way, I'll tell you this: when I was studying ECE at UMass, in 80 to 84, started out in computer engineering, then I moved into electrical, but I could never learn something directly or understand anything ever in a lecture, not ever, not once. I don't think I was ever able in class to have someone throwing this kind of material at me and having me internalize it, digest it, make sense of it in real time. Not ever. What I would do instead is I would sort of hear it all in, I'd have it wash over me, I'd take notes, or I'd have the notes, and I would say, okay, this is what I have to be learning now. And it wasn't until I went home later on that I would study it and think about it and code it. That's when I started to make sense of it. So, and different people process information in different ways, but I've had, many students tell me that they have a difficult time learning this in lecture, and indeed that's the case. That's not when you learn to code. You learn to code when you write it. But anyway, this next bit here, or this next part, how do you set, when we say, by the way, when we say set a bit or clear a bit, what do we mean? Set a bit means make it 1. Clear a bit means make it 0. All right. Toggle a bit means, if it's 1, make it a 0, and if it was a 0, make it 1. Okay. So how do we set a bit using an OR mask? You just OR it with a mask that has a bunch of zeros and then a 1 in the position you're interested in. And what that will do is that'll cause that bit to get set. Okay, so these become sort of handy dandy tools that we use to go in and set or clear individual bits without impacting the other bits in the byte. That's the important thing here. That's the money here, right? It's not that we're setting or clearing a bit. Anyone can do that. It's that we're setting or clearing a bit without changing the other bits in the byte. This is what allows us to be surgical about this. Okay, the idea of when you have an initial value, an initial byte, and you go in and you end it with a mask that has a hole in it, you're surgically going in and you're zeroing out 1 bit without touching the other bits. Likewise for an OR. Okay, so that's what's important here. You're able to set or clear bits without messing with those other bits. Likewise, if you want to toggle a bit, do the same thing, right? You're just going to use an exclusive OR. If there's a particular bit that you want to toggle, let's suppose I want to toggle that bit in that position right there. What I would do is I would exclusive OR it with a mask that has a 1 in that position. And that's going to take that. If it's an original 1, it's going to turn it to a 0. And if it was originally a 0, it'll turn it to a 1. So you can toggle a bit using by doing an exclusive OR with a mask. Okay, just a little bit about language here, nomenclature. You'll hear people refer to this first group of these bit level operations as binary operators, and it's by binary we mean 2. Binary means 2. Okay, today is 2, 22, 22, right? These operate on 2 different operands. So for example, A and B, A or B, A exclusive or B, and those are 2 byte level operands. There's also the inverter here, right? Another gate. You know what an inverter is from ECE 124. That's a unary operator. It only operates on 1 operand. So if you use tilde B, that's the inverter. What that'll do is it'll invert each and every bit in a byte. So if you start out, for example, with, this byte here, right? This pattern of 1s and 0s, and then you said, let's let Z equal the inverse of Y, right? Then that would you would invert every single bit. So that's the idea. When you invert, a 1 becomes a 0, 0, right? 0 becomes a 1, and so forth. So don't confuse this inverter operator with the not operator, right? You can, when we tested for equality a couple weeks ago, we wanted to say if A equals B, if variable A equals variable B, we use 2 equal signs. We were testing logically to byte size or to word size values. Or if we wanted to see if they were unequal, we would use parenthesis equal. That was the not equal. This is different, right? Those other operators operate on they're logical operators, and they compare 2 objects for equality or inequality. Objects can be bytes they can be ints, they can be long ints, and they were checking the entire object at once. Here, we're dealing with bit level operators. So they go in and they work on the individual bits. So we have the inverter here. So we have all these operators that we can work with. Okay. All right. One more to show you, and this one is the most confusing to sort of make sense of and digest. And then once we have that, we'll start applying this. This is the shift operator. Okay. And so when we have what looks like, it looks like two nested greater than signs, right? That's the right shift operator. And if they're pointing the other way, that's the left shift operator. And so the idea is that if we have some data, we'll start out with some data. That is a byte, a pattern of ones and zeros. And what we're going to do is shift that pattern of ones and zeros to the right a certain number of bits or to the left a certain number of bits. And it's easiest to show this with an example. Suppose I do this operation. All right, 1 1 1 0 0 0 0 0, and I do shift right 3. I just take that whole pattern and I shift every bit to the right 3-bit positions. Okay, so for example, this 1 shows up over here, right, and the second one shows up over here, and what happens to this 0? Well, that sort of falls off a cliff. It's gone, right? This one here is also gone. Right, so you're shifting them all over, and if they shift out of the end of the byte, then they're gone. They're lost to us. Okay, that's if we shift right. If we shift left, so if I take the number 1, right, just the number 1 in decimal, which is this pattern 0 0 0 0 0 0 0 1 in binary. If I shift that right 2 positions, this is what I get. I just shift the whole thing right. I'm sorry, left. I shift it left 2 positions. Let me just say a word about why, when I show things in binary, why am I showing that space there, right? The binary word is 8 bits. I tend to show it as an upper nibble space and a lower nibble. That's just for the benefit of our eyesight. Because if you don't have that space in there, it can be hard to actually see how many zeros that you've got, how many ones that you've got. So it's just for our visual convenience that I put that space in there. Okay. This one's going to be confusing, but the idea is you take the whole pattern of ones and zeros and you shift it to the right or left. So here's an example. And yes, Sebastian's asked a question. So it means you pad zeros to the left or right, if as needed. That's what happens. You end up, if we look at this example here on the left, right, we're shifting everything over to the right and we're filling in zeros all the way over on the left side. And in this example on the right, where we're shifting to the left, we're padding, we're filling in with zeros on the other side. So what does this represent? If I say 1 left shifted 3 places. Well, this is a little confusing because this is what 1 is, right? 1, just written as 1, means 1 in decimal, right? And if we shift that to the left, 3 positions, right? Then we're taking this pattern of zeros and ones, and you see how I'm not separating the nibbles here, so it's really try to count the number of zeros there with your eyes. It can be tricky. Anyway, you shift that left 3 times, and what happens is that this 1 moves into this position here. Okay, so 1 shift left 3 is the same as this. 1 shift left 7, I'm going to move it all the way over, 7 positions. 1 shift left 0 is the same as 1. There's no shifting. Okay. Now, let me show you a tricky one. What about 0 shift left 3? So 0 is just 0 in decimal. If we represent that in binary, that's just 8 zeros. And if we shift that over 3 times, we still get zeros because we're just shifting a bunch of zeros. So 0 shift left 3 is the same as 0 shift left 7. It's the same as 0 shift left 0. There are no ones in there. So all you're doing is you're shifting zeros over and you're filling in when you have empty spots. Okay. So now we're gonna make use of all this. So we're gonna sort of put all this together. So how do I go and I set a particular bit in a byte? Okay, so someone's asking, what happens if we do a right shift and then a left shift? Do we get back to the original value? No, not necessarily. You don't, because when you shift something right, you could have some low order bits that fall off the edge, and then when you shift left, they become zeros, so you don't get them back. Okay, it would be analogous to a shift left operation is equivalent to multiplying by 2. And a shift right operation is equivalent to dividing by 2. Now, when you divide an int by 2, you throw away the remainder. So let's think about what happens if you take an int and you multiply by 2 and then divide by 2, do you get back the same value? Well, as long as you don't overflow the size of the word, you do. Okay. So let's suppose that we're dealing with an unsigned int, an unsigned char type, unsigned char, which would be an 8-bit integer that can store numbers between 0 and 255. And so suppose you have the value 10. If you multiply that by 2 and then divide that by 2, do you get back where you started? Yes, you do. 10 multiplied by 2 is 20, divided by 2 is 10. But suppose you go the other way, 10 divided by 2. Oh, well, you're going to get 5. But if you had 5 divided by 2, you're going to get 2.5. You're going to throw away the integer part. That's what can happen when you shift to the right. You're throwing away the fractional part of an int. So when you shift right and then shift left, you may not get back what you started with. So you want to be careful if you're using a shift operator to do multiplication. Likewise, if you shift left and then subsequently shift right, as long as you don't overflow, you'll get back what you started, but you may get an overflow. All right. So, all right, that was a digression here. So let's take a look at how we go about setting a bit in a byte. And what we want to be able to do is go to one of these ports, right? And we just want to set a particular bit and leave the other bits alone. Right? We want to leave them untouched. So we're going to make use of the things that we've just been talking about. So let's concentrate on this first one here. Okay. We're going to make use of the OR operator and a mask to set a particular bit of a byte to 1. So let's take this command right here. Suppose I take port B, which and it has. We've previously done something with port B. We've set certain values high or low. But what I want to do now is I want to set one particular bit. I want to set bit 4. Okay, and the bits starts out with bit 0. The bits are counted 0 through 7. So when we say bit 4, we really mean the 5th bit, right? But that's a little confusing. I won't always do this, but I just want to remind you that bit 4 is bit position 5, because it's bit 0, bit 1, bit 2, bit 3, and bit 4, because we number them 0 through 7. But in this command here, what I want to do is I just want to set bit 4. I want to make bit 4 high, and I want to leave all the other bits untouched. So all I do is I take port B, and I set that equal to port B or this mask. So what will happen is it'll go in and it'll operate on each and every bit in port B, right? When you OR something with a 0, it leaves the bits untouched. When you OR it with a 1, you get back 1. So this has the result of setting bit 4 of port B. Okay, and it leaves all of the other bits of port B untouched. So that's why I have this statement over here. Okay, it sets port B4. When we say port B4, that's another way of saying bit 4 of port B. Okay, that's all we mean. So this is a way of setting that high, leaving the other bits of port B alone. Okay, and why is that important? Well, suppose that bit 4 is used to turn on an LED, but bit 5 is used to launch a missile. Obviously, you want to be able to turn on the LED without impacting the launch of a missile. Or something less dramatic, bit 5 is used to turn on my morning coffee, right? But it's important, obviously, to be able to set these individually, okay? From this first line to the next line here, it's the same thing, but I'm just using shorthand. I taught you this shorthand earlier. C coders, the cool kids in C, like to use this kind of shorthand. So another way of saying port B equals port B or something, we write port B or equals. So they mean the same thing. It's just cool kid shorthand in C, right? Everyone does it. So these mean the same thing. Now, another way of doing this, all right, now we're talking about really some cool stuff. These two things here, right, almost look like a pair of eyeglasses here. But these two things are two ways of doing the same thing. If I want to create this mask, instead of typing in this pattern 0, 0, 0, 1, 0, 0, 0, 0, I can just write 1 shift left 4. If you take a 1 and you shift it left 4, that's the same as 0, 0, 0, 1, 0, 0, 0, 0. So as a consequence of that, this third line down here, port B equals port B or 1 shift left 4. This is another way of setting bit 4 of port B. And then when we get to the, what the cool kid shorthand here, port B or equals 1 shift left 4. That's the way you would read this. Port B or equals 1 shift left 4. What that'll do is it'll set bit 4 of port B. It'll set port B4 and it won't touch the rest of the bits. What about this down here? Well, I'm going to be setting bit 4, and bit 3, and bit 2. I'm ORing, right? So I'm ORing this with a 1 in this position, or a 1 in this position, or a 1 in this position, right? And this confection here, 1 shift left 4, or 1 shift left 3, or 1 shift left 2, is putting a 1 in positions 2, 3, and 4. So this would be the line that we would use to set B2, B3, and B4 high and leave all the other bits untouched. Okay, so I mean, it's really not complicated, but the coding gets a little gnarly, right? Okay, that's setting a bit in a byte, making it go high, and we're just making use of ORing it with a mask. Okay, how do we clear? Oh, go ahead.
I have a question that was direct message to me, but I think it's useful.
Okay.
Does it also work to shift zeros left and right? So could you say 0 shift left 3?
0 shift left 3 is 0, because all 0 is just 8 zeros, right? When we say 0, we by default we mean in decimal, but 0 in binary would be written 0B 0 0 0 0 0 0 0 0. And you can shift that right and left all day long. All you're doing is shifting around zeros, right? So there's no change. So 0 shifted is still 0. Okay.
Thank you.
Okay. All right. So now we're going to be clearing a bit. And we saw that if we AND something with a mask that has a hole in it, right, a 0 in a certain position, we can use that to clear a bit of a particular byte. So we'll start out with this line here. Suppose I have port B is equal to port B, and I'm ANDing it with a mask that has a hole in it, or a 0 in this position. When you AND something at bit level with a 1, you get back the original bit. But when you AND it with a 0, the result is 0. So this has the effect of clearing bit 4. All right, it clears. And when we say clear, we mean set that equal to 0 or make it equal to 0, right? And sometimes we're precise, and sometimes we're imprecise about the language here. So when I say clear a bit, I mean make it go low. But if I say set a bit, I mean make it go high. But sometimes we'll use the language differently. We'll say set this bit high or set this bit low. So we're using the terms set and clear kind of imprecisely. And when I mean a certain thing, I'll try to make that clear to you. Okay, but basically this first line just shows us how we can clear a particular bit. And this is all we're doing here. Okay. Now let's show you how to do this with with the shift operator, okay? This is the same as this way over here on the right. I just copied that over, okay? But what I wanted to show you, moving from the right to the next position, right, in here, okay, this mask here is just the complement of this mask. So I have 1, 1, 1, 0, 1, 1, 1, 1 is the complement, the bit level complement of 0, 0, 0, 1, 0, 0, 0, 0. And the reason why that's nice is I can easily express this as 1 shift left 4. So the result is I can achieve this same line. Well, of course, I can achieve it this way using the, using the shorthand, but I can achieve it this way, port B and equals complement 1 shift left 4. Now that's a tough thing to sort of unpack in real time. Okay, someone's asking, why is it clear bit 4, but it's the 5th bit? It's because we count the bits from 0. Right. So the question is, why is it that we're saying we're clearing bit 4, but we mean the 5th bit? We have bit position 0, bit position 1. Let me not do it this way. Let me just look at, let's look at this byte here. Okay. That's bit 0. That's bit 1, bit 2, bit 3, and bit 4, starting from 0. So I probably shouldn't even say the 5th bit, but I just want you to appreciate that it is the 5th bit from the left, knowing that we start with bit 0. Okay, and this is something that'll come up again and again in C. C likes to start at position 0. You'll see this when we're dealing with arrays. In C, you index an array starting with 0. Right, and going up to n-1, where n is the number of elements in the array. I don't want to digress too much about that. Okay, so we've looked at how to set and how to clear. What's next? How to toggle. You knew this was coming. Okay, and the way we toggle is we use the exclusive OR operator. So it's the same game now, right? Let's suppose I start out with a particular byte that has these values x, and x can be anything. They can be 1s, they can be 0s. If I then exclusive OR that with this mask, that has a 1 in this position, then the result is all those other bits get unchanged, but that bit position gets toggled. So that's what I mean when I put a bar over it, right? You remember that probably from 124. That's my way of representing that I'm toggling it. So if it was a 1, it becomes a 0. If it was a 0, it becomes a 1. So this would be our statement. Port B is port B and exclusive OR. I give it a mask, and I put a 1 in that position, and we're toggling that bit. Here's the shorthand notation, okay? And by now we sort of recognize we can take this and just represent that as 1 shift left 4. Okay, so this is how you talk embedded C, folks. Okay, so this is how we set PB4 equal. Well, this is incorrect. This should not say clears PB4. It should say toggles PB4. All right, there's a lefty writing the word toggle, but that's a typo. It toggles PB4. If it was a 1, we make it 0. So we've just looked at how to set and how to clear and how to toggle individual bits without impacting the other bits in the byte. That's the important thing. Okay, I want to digress a little bit here. So, well, let me actually, before I do, let me just pause and ask, do you have any questions on this? Okay.
Right here in front row.
What would happen if you tried to do like with the shorthand? What if you tried to do like 1-1 shift left 4? Would it be able to handle that, or
Yeah, 1-1 shift left 4, right? 1-1 is just 0 0 0 0 0 0. Let's see, 0 0 0 0 0 0 1 1. Okay, so you would just take that whole pattern and shift it left.
Okay.
Now, if you did it here, right? So I'm answering your question strictly as a shift left operator. right? You would just get that pattern, and you'd still have a 1 and a 1-1, but they'd be shifted over to the left, let's say 4 positions. The particular tactic that we've got here is we're asking, how do we go in and set, clear, or toggle 1 bit in a byte? And so the way you do that is you're just shifting 1 left to the left is what we've been doing, because we're making a mask. And a mask is a device that we use. You put a 1 in a particular position, and you use it to set or clear or toggle. Right, so this is just one of many uses of the shift left operator, right? And I think where your question may be is, what would happen if we were to create a mask that had more than one in it? And we could do that. It's something different though, right? So here we're looking particularly at a tactic that we can use to go in and in a compact way, set, clear, or toggle 1 individual bit. And so the recipe is, either you build a mask. How do you build the mask? You just take a 1 and you shift it. Okay. All right. I want to show you different ways that people sort of language this. If you look at code, you'll see people write this in slightly different ways. And so I pulled as an example an example from the textbook, and it's way up in chapter 7. So it's sort of in the future. But I just wanted to show you this. Let's look at what it does. Write a C program to toggle only the port B 0.4 bit continuously every 1 millisecond, and use the timer in normal mode, blah, blah, blah. So ignore everything about the timer. Ignore that, right? So we can ignore everything here that has to do with the timer. I just wanted you to see, ignore everything about the timer, okay? I just wanted you to see, first of all, to see an example of what we've been talking about just now, right? So it's toggling port B4 continuously. So look at the way the code is set up. So first, we have DDRB is 0xFF. That means we've set every pin in port D as output pins. And then we go through the loop, and then every time we go through, we're toggling PB4. Okay? We're toggling PB4. So every time you go through the loop, you know, if it was high, it's going to be low, and if it was low, it's going to be high. The rest of this is a delay so that you're actually making it toggle at a certain rate. All right, but what I want you to notice is the different ways that this code refers to bit 4 of port B. Okay, so first of all, notice, look at the way the author chose to write this. Toggle only the port B 0.4 bit. So they call it the port B .4 bit. Okay. Then down here in the comment, they write toggle PB4. So they're referring to it as PB4. And then in the actual shift operation, they're using a 1 shift left 4. So they're kind of using all of these notations to refer to that. Okay, I've got a question. Is caret, is this hat, is that the toggle operator? No, that's the exclusive OR operator. We get toggle when we exclusive OR with a mask. Okay. But what I wanted to show you, what I wanted you to glean from this example is that I mean, we know what's happening in the code, right? We're making pin 4 of port B go high and low, high and low, high and low. That's what's happening. And so I wanted to just show you with some registers here what happens as we pass through this while loop. So the first time we go through the while loop, this is what's going to look like. We haven't previously set port B to any initial values, right? All we're doing is we're telling port B to toggle pin 4, right? Or you know, port B4. Where we want to toggle port B4. We're not giving instructions for any of the other bits. So I've got X's in there. They're left undefined, right? In actuality, they will all power up as zeros. That's what will actually happen, is they'll power up as zeros. So, but I'm calling them X's because we're ignoring them. We're only focusing on what happens with port B4. So when we hit this statement here, right, the first time we hit it, we're going to have a 0 in position 4. And so, and that refers to port B4. That's the data register for port B. If we actually looked at PB itself, that means the pin, the physical pin. If we went up to that pin with a multimeter, and we've connected a multimeter to look at that voltage, it would be 0 volts. If you want a multimeter, a pocket multimeter, go get one in the lab and have it and keep it, it'll be yours. Okay, we got them in the lab for you. Go get one, but if you want to do this. So the first time through this thing, PB4 has value 0 volts. The next time we go through the loop, we've toggled. So port B4, that is the logical value in the data register for port B, pin 4 becomes a 1, and that corresponds to 5 volts on the pin. And I'm going through all this in detail to sort of show you the difference between the logic value corresponding to the pin, that's a 0 or a 1, and the actual voltage, it's a 0 or a 5. The next time we go through, the logic value has gone from 1 to 0, and the voltage is 0. The next time we go through, the logic has become a 1, and the voltage has become a 5. Okay, so that's what's toggling, right? We're operating on this individual bit. Now, how should we refer to this? What should we refer to? Should we refer to what's happening as PB4, port B4? How do we refer to it? And so what I wanted to point out is in this example code, they're kind of referring to it sort of simultaneously as PB4 and port B4, right? What's actually being toggled is the bit in the port B data register. And then as a consequence of that, the hardware, which is a flip-flop, is itself toggling high and low. So they're kind of both being toggled. But the way the textbook author wrote this is kind of being casual about simultaneously referring to this as PB4 and port B.4. Okay, so going further down the rabbit hole here, I wanted to introduce, for the first time in the course, the data sheet for our chip. And I've posted the data sheet to Moodle. This, some people believe that the way to teach this course is to not have a textbook, but rather give you the data sheet and say, here's an assignment, here's the data sheet, go figure this out. That is one way of teaching the embedded systems class. And you learn to read the data sheet the hard way, and it's important for you to ultimately be able to read the data sheet. My own experience in giving you the data sheet as the primary text instead of a textbook, it would be like, let's suppose that instead of this class being about learning embedded systems, maybe this is a class in French, and I'm teaching you French. And maybe this is your first French class, so this is French 1. Maybe you haven't taken it in high school, and this is French 1. And so I hand you a book of French poetry or a novel from literature, and I say, here, read this and discuss it. And you're trying to do that in French 1. It's a tough way to learn French. And likewise, it's tough to learn embedded systems from the data sheet. But at the same time, you've got to learn how to read the data sheet. So my approach here pedagogically is we've got the textbook. I'm walking you through this stuff with these words and these slides, and I'm going to be pointing you into the data sheet from time to time so that we can give you some skills in learning how to read the data sheet. But the thing about learning to read one of these things, it's like joining the middle of a very technical conversation that's been going on, and from the get-go, you're trying to make sense of it. Right, that's the problem. You don't have any prereqs, and they speak as though you have been coding in expert systems for 5 years. That's what it's like reading a data sheet. So just know that, okay? And I'm going to have more to say about the data sheet as time goes on. But I wanted to show you a particular thing in the data sheet. If you go to the chapter where they describe the I/O ports, right, and using, by the way, using using any of the modern PDF editors, like using Adobe, right? Then the data sheet, which runs to several hundred pages, it's indexed in such a way you can just open up the left side panel and tell it, let's go to the IO ports. And it has lots of dense information there. But I wanted to show you how the data sheet describes the different ports. So here's port B, which is the port B data register. DDRB is the port B data direction register. And then pin B, which is the port B input pins address. So these are the registers that describe port B. Then you also have the registers for port C, okay, and the registers for port D, and so forth. Okay, and I'm going to show you that again on the next slide. So I'm going to just take that and I'm going to kind of blow that up. So this is how the data sheet describes those particular registers. And it's being very deliberate about this. Port B is a register. It has a certain address that you can speak to, but it's not something that we need to know, because when we program, in C, we have an include file at the top of all of our code, include avr/io.h. And what that does is it gives us kind of a nickname for this register. So we don't have to actually ever know the hex address for the data register in memory corresponding to port B or for any of these ports. Those are all defined with define statements in the header file resulting from include avr/io.h. So that's the first thing. The next thing is, how does it describe the individual bits in these registers? Well, in a way that makes sense, right? Bit position 0, they call it port B0, port B1, port B2, and on up through port B7. Okay, that makes sense. So when you're talking about the individual bit positions in the port B register, you call them port B0 through port B7. Likewise, for the data direction register, they're called DDB0 on up through DDB7, right? And likewise, the input pins, pin B0 on up through pin B7, okay? So now look down the bottom here. I just want to review the terminology here. What we're talking about, we have the actual pins themselves. These are the pins on the chip that you have access to and you connect things to. This is where these pins connect to the outside world. So those are the hardware pins on the chip. And then these here represent software. These all represent locations in memory addresses. So your code interacts with all of these on the right, and then your hardware interacts with these. Each of these fills up one 8-bit byte because we're dealing with an 8-bit microcontroller. So each of these has associated with it an 8-bit, 8 bits of information. Question? Okay. Now we get to the sort of the final thing, all right? Each of these corresponds to a bit position, right? Let's take port B0. That just corresponds to bit position 0. DDB0 corresponds to bit position 0, and pin B0 also corresponds to bit position 0. That makes sense, right? They all correspond to, a bit position 0, 1, 2, 3, 4, 5, 6, or 7. Okay, here's the next slide. It turns out that you can use commands like we just did, right? I can write DDRB is equal to 1 shift left 5. What that's going to do is it's going to cause bit position 5 to be high, and all the rest are going to be 0. And I can do that with DDRB. I can do that with port B, right? And by the way, when I write something like this is different from what I just did. Before I was setting 1 bit, and I was using a mask, and I was leaving all the other bits untouched. If I do this, DDRB equals 1 shift left 5, I'm going to end up with, that's bit 7, bit 6, bit 5, bit 4, bit 3, bit 2, bit 1, and bit 0. That's what this is what I'm putting in there. Okay, so if I did that line there, that would make this an output pin, and all the rest are input pins. And this is what we just looked at. It's just a little different way of doing it. It turns out you can achieve that same result by writing this. Instead of, when you talk to DDRB with 1 shift left 5, you can achieve the same thing by writing DDRB is equal to 1, well, that should say shift left, DDB5. Now, why would you do that? You only do it to make the code look nice. It's just done for precise documentation. These mean the same thing. And why do they mean the same thing, and why do we do it? It turns out in this include, the result of including this at the top of your code, you will actually get a define statement that says this. It just creates DDB0 as a symbolic constant equal to 0. So every time you have DDB0 in your code, the preprocessor replaces it with 0. Every time you have DDB1, the preprocessor replaces it with a 1. Every time you write out port B0, the preprocessor replaces it with a 0. So down here, DDB5 is the same as 5. It means the same thing as 5. Port B5 means the same thing as 5. And so the compiler won't care, the chip won't care. This is a style or programming, documentation, and understandability issue. And I believe this will make sense to you when I go to the very next slide. Okay, so I already showed you this slide, right? I showed you slides for setting a bit and a byte, clearing and toggling, right? I'm showing you those same slides now. I'm gonna go forward and backward with the slides for a minute, all right? So we're on slide 23, but we have setting a bit and a byte, clearing a bit and a byte, and toggling a bit and a byte. The same slides that we showed. It's just that now I've introduced this new nomenclature. I've just introduced this. So we already looked at the slide. This is the only thing that's different about it. Another way of saying port B or equals 1 shift left 4, we can write port B or equals 1 shift left port B4. It just makes it more clear what you're doing. It means the same thing, because there's a define port B4 for statement up in that header file. And so when you look at port B or equals 1 shift left port B4, it's once you get used to this, you can immediately understand it's a nice self-documenting way of writing this out. And so if you look down at the very bottom here, these are 2 ways of achieving the same thing. I'm setting port B2, port B3, and port B4 high with this statement down here. Okay, that's setting a bit and a byte. I'm going to go to the next slide. Clearing a bit and a byte. We already looked at this, but I've just added this line to it. So I'm just introducing this new way of writing this. They mean the same thing, right? The difference is port B4 is defined via the include AVR /io.h. You always put that at the top of your code. You're wondering why we do that. It defines all these things for you. All right. And so it's just a way of making the code easier to understand. So it's a programming style issue. Okay. Same thing for toggling a bit in a byte. Okay. Just some examples to sort of, let us end this Tuesday afternoon with a sense of satisfaction. Let's and I call this example 3 because I'm sort of treating the previous set of slides. I had examples 1 and 2. So this is sort of the examples associated with GPIO. All right. So let's suppose I have a 7-segment LED that's connected to port D. Right. I want to display 1 on the segment. Okay. So you have in your kit a 4-digit 7-segment LED. And the way those things the way they work is you they have 7 segments on them, and you light up the different segments based on what kind of a digit you want to illuminate. And the segments are numbered 0, 1, 2, 3, 4, 5, and 6. 7 is actually a decimal point off to the side. So, and so you have, let's say we have port D. We have 8 wires from port D going out to, well, I guess to make this consistent, I'm going to put a 7 there. That'll be a decimal point. Okay, that's 7. So we have 8 wires from port D. We're using D0 through D7, and they're physically connected to 8 wires on this LED. So to sort of make this make sense, it's a 7-segment LED with a decimal point, right? That's what that means. I'm trying to sort of rationalize how we have 7 segments but 8 wires. It's with decimal point, with DP decimal point. And indeed, you have that on your device. If you look at it, you'll see a decimal point. So you have all 8 wires from port B wired out, and all we want to do is we want to cause 1 to show up on this thing. So all that means is we want to illuminate D1 and D2, and we want to leave the other ones off. Right? So this is what we want to do. We want to write code that's going to first set all of those pins as output pins. Then we want to cause these 2 pins to glow, to go high, right? And the others to stay off. So we can write it different ways. So it's just a program segment. We could just write it in binary, right? Make them all high as output pins. And then these are all low corresponding to pins off. And then these pins 1 and 2 would be high, making those pins have 5 volts, causing those LED segments to glow. Right? It's hard to do things in binary because a lot of 1s and 0s to keep track of. It's easier to do it in hex, right? So I can write 0xFF, and I can use the shift left that we've just been dealing with, turning 1 and 2 on. Or I can use sort of this preferred nomenclature that I just showed you, right? Turn port D1 on and also put port D2 on with that OR statement, okay? And just to review that, right, why does that work? Why does this work here? I'm showing that down in the bottom here, right? If I take 1, when I write 1, this is what we mean. 1 is just 7 zeros followed by a 1. 1 shift left 1 means you just take that 1 and you move it over 1 spot. 1 shift left 2, you move it over 2 spots. And if I do 1 shift left 1 or 1 shift left 2, right? I'm taking this result and I'm ORing that with this result, and I end up with 1 in each of those positions. Okay, so this is bit level manipulation. This is bit twiddling, but we are down in the bits here, right? Using C manipulations to make the bits do the things that we want. Okay, the last example here that I'll give is, let's suppose we want to cause the digit 3 to glow on one of these things. Okay, and by the way, in my coffee pot with my display, in anything that you have that has a digital display that has digits is doing this. So anytime you look at clock displays on your watch, anything, well, actually, watches have organic LED displays. So, but anything that has your classic 7-segment LED display is doing this kind of thing. All right, if we wanted to make a 3 show up on there, then we would have to activate bits 0, 1, 2, and 3. Okay, so we want 0, 1, 2, and 3 to be set high. So the code here, we could do it this way. First of all, make all the pins output, and then 0, 1, 2, and 3, or we could use this structure down here. Okay, and let's see. Someone's asking, what about 6? 6 is, oh, you're right. You're right. 0, 1, 2, 3. You're right. I'm missing the 6. I think Tyler has correctly pointed out that I also need to have 6. So I need to have 0, 1, 2, 3, and 6. 0, 1, 2, 3, 4, 5, and 6. I would also need this. It appears that this is the case. So I would also need to have 1 shift left 6. All right, that's my horrible left-handed use of a right-handed mouse, right? And then down here. 1 shift left, port D6. Okay, port 6. Okay. We can leave it at that for today. That's a lot. Tomorrow's lecture, we're going to look at this. This was all about setting pins high or low and going and setting individual pins high or low and toggling them. Tomorrow is going to be about reading pins. So how do we read input pins, and then we'll put it all together with switches and LEDs. Okay. Okay, Anthony asked a question. If you make a pin an input pin, can you accidentally set clear or toggling by bit twiddling wrong? C will let you do all kinds of things wrong. So C is a language that trusts the